This is a screencast on how to assess whether or not a molecule is polar. So it's molecule polarity. We're trying to figure out, is a molecule polar or is it non-polar? And the two things you have to look at to try and make that assessment are you have to look at the bond polarity that's present in the molecule and ask, are the bonds polar? And then the second thing you have to examine is the shape. So first we look at the bonds, and then we look at the shape. So there's lots built into that. There's a lot of pre-existing knowledge you have to have in order to properly figure out if the bonds in a molecule are polar. And of course you have to remember what the shapes of molecules are like based on the number of electron groups around the central atom. So you first have to make sure you understand bond polarity and you understand how to figure out the shape of a molecule. And if you feel like you're confident in that, then we can move on and start trying to properly assess whether or not a molecule is polar. All right, so let's let's take, for example, a molecule like CH4. Okay, CH4 is methane. Of course, we first have to put together the Lewis structure for that. Carbon has 4 valence electrons. Hydrogen has 1 valence electron, and there's 4 of them for a total of 8 electrons. That's of course valence electrons. And so that's the total batch of electrons that we need to make sure we show in the structure. So carbon is going to go in the middle, 4 hydrogens around it, single bonded, and then we put in any necessary lone pairs. And of course, lo and behold, when we count the bond pairs that are there, we see there's 2, 4, 6, 8 total electrons already. So we don't have to put in any lone pairs for this. This is the proper Lewis structure for methane. Now, let's figure out, is this thing polar? Is this molecule polar or what? So first examine the bonds. Every bond is the same in this molecule. It's the CH bond. Is the CH bond polar? Well, remember what it means to be a polar bond. It means that there's a difference in electronegativity between the two atoms, and thus they will not share electrons equally in the bond. One of the atoms will pull the electrons closer to itself than to its neighboring atom. So in this case, if you look on the periodic table, you'll see that carbon is more electronegative than hydrogen. So the electrons, this is not any official notation, but the electrons would be pulled in each respective bond slightly closer to carbon. Okay? So the bonds are polar. Is the molecule polar, however? Well, if we look at the shape of this molecule, because it has 4 electron groups around the central atom, 1, 2, 3, 4, the shape is what we would call tetrahedral. Each of those 4 electron groups are bond pairs, so it makes a tetrahedral shape. In other words, like the carbon is like dead in the middle of this molecule, and it would kind of be making a triangle-based pyramid in a way that we call, well, it'd be an equilateral 4-sided polygon, a tetrahedron. So we call it tetrahedral. So actually, each point on that tetrahedron would be out here at the hydrogen, okay? And each of those hydrogens would kind of be equally partially positive because they've got electron density pulled away from them. So in this case, because the shape is tetrahedral, all the bonds are the same. Even though the bonds are polar, this is a non-polar. Let me maybe put a different color in here for this. This would be overall a non-polar molecule. Let's do another example. Water. Water, you hopefully remember just off the top, is polar. This is a polar molecule. You should just, with familiarity, remember that. But let's build in some support using the proper methodology and support why it's a polar molecule. Okay, so again, Lewis structure. Oxygen has 6 valence electrons. Each hydrogen has 1. There's 2 of them. That's a total of 8 valence electrons we need to make sure that we show. Put oxygen in the middle, connect it with at least 1 bond with each of the substituents. We've shown 4 electrons. We need to add 2 sets of lone pairs. for a total of 8 electrons. That is the proper Lewis structure for water. Are the bonds polar? Yes, they are. Of course, anytime the atoms are not the same atoms, there's going to be some polarity in the bond. Because if the atoms aren't the same atoms, like hydrogen and oxygen are not the same, they're not like O2 where they're both the same, that's a nonpolar bond. Or they're not like H2 where they're both the same, that's a nonpolar bond. Or they're not like N2 where they're both the same, that's a nonpolar bond. Okay, I'll stop doing this. But I will properly fill out the Lewis structures. I can't leave it naked like that. So this is a polar bond. OH is a polar bond for sure. But there is no but. Sorry, it's a polar bond because they're not the same atoms. Okay, so we're gonna have a little bit more partial negative charge down by oxygen. We're gonna have a little partial positive charge up by hydrogen. Okay, what's the shape of the water molecule? Well, there are 4 electron groups. 1, 2, 3, 4 around the central atom. 2 of them are lone pairs. So we say that the shape of this thing is bent, or maybe you prefer to say V-shaped. Also okay. All right. So it's a bent shape with polar bonds. And what we would see in this bent structure, okay, so I'll kind of draw just a little image of the bent structure up there. One end of that bent structure is going to be partially negative down here, and the other end is going to be partially positive up here. And that's because the electrons are generally pulled to this end. So up here is going to be positive and down here is going to be negative. So this is confirms that this is a polar molecule. It has a positive end and a negative end in like 3-dimensional geometrical space. Let's do another one. Let's do CFH3. Is that how I meant to write that? Probably not. CH3F. Okay. Carbon has 6 valence electrons. No, it doesn't. Carbon has 4 valence electrons. And hydrogen has 1. There's 3 of them. And fluorine has 7. All right. So this is a grand total of 14 valence electrons we need to make sure we show in the structure. Carbon's going to be in the center, connected to each thing by at least a single bond. All right, we've done 8 of those 14 valence electrons. So thus we are down to, we have to show 6 more. So 6 more valence electrons is going to be 3 lone pairs. We're going to put them all around fluorine, because that way we can honor the fact that fluorine had 7 valence electrons to begin with. So there's its 7. 6 of them are lone pair electrons, and 1 of them is shared with carbon. All right. So now we do the 2 things. We analyze bond polarity and we analyze shape to try and figure out if this molecule is polar. So are the bonds polar? Sure they are. They're going to pull, this one's going to pull towards carbon. That one's going to pull towards carbon. That one's going to pull towards carbon. But how about the bottom one? It's actually going to pull towards fluorine. If you look up the electronegativities, and you hopefully maybe remember, fluorine on the top right is the most electronegative atom on the periodic table. So electron density is going to be pulled down towards fluorine here. So we're going to see that this is partially negative. This is partially positive. This is partially positive. This is partially positive. Okay? So is this molecule polar? Well, its shape is tetrahedral. Hopefully that makes sense. It's got 4 electron groups around the central atom. They're all bond pairs, tetrahedral. And so we will see a dipole, or we would say this molecule is indeed polar. It has a positive end at the top. It has a negative end at the bottom. Okay? So overall, if you were approaching this tetrahedron out there in 3-dimensional space, this end of it would be overall negative, and this end of it at the top would be overall feeling more positive. There's a greater electron density at the bottom. Thus, this molecule is polar. How about one more? You want to do one more? Let's do one more. CO2. CO2, is it polar? Carbon, 4. Oxygen, 6 times 2. For a total of 16 electrons. right? Carbon in the middle, connected to each oxygen. Let's make the proper Lewis structure here. We have used 4 electrons, right? So we need to represent 12 more. So it looks like we need to put 6 lone pairs around. So let's do it. 1, 2, 3, 4, 5, 6. You could stop there, but there's a problem with this Lewis structure. And the problem is that carbon does not have a full octet. It's not obeying the octet rule. More electrons need to be shared with carbon here to satisfy the fact that carbon had 4 valence electrons to begin with. It's not doing like 2 random coordinate covalent bonds out with the oxygens. It doesn't really make energetic sense. Instead, more electrons need to be shared with the central carbon. So let's take a couple of these lone pair electrons and instead create a couple of double bonds. And that's what we find in the carbon structure, in the CO2 structure, is that we have a double bond on each side. That's the proper Lewis structure. So are the bonds polar? Yes, they are, because carbon and oxygen are not the same atom. So the electrons are going to pull in that direction, electrons are going to pull in that direction. We're going to have partial negative out here, we're going to have partial negative out here, and then in the middle, we're going to have partial positive. But that gets kind of hidden because it's in the middle, and the shape of this molecule is linear, right? 2 electron groups around the central atom, both bond pairs, it's linear. So actually, if you approach this molecule, this end is going to feel partially negative, and this end is going to feel partially negative. So can we draw a dipole on this thing? No, we can't. There is no like positive end and negative end. There is like a positive, partial positive charge center, but that's not really exposed when it comes to how this molecule interacts with everything else in its environment. So there's no real positive and negative end on this thing. And so in the end, we would just surmise that this is nonpolar. Okay, this is a nonpolar molecule. One final word I'll say about molecular polarity is when we're doing Lewis structures, we also do it for polyatomic ions. Polyatomic ions, and in fact any ions that you encounter are always polar. Always, always, always polar. And that's because of how they interact with everything else in their environment. So you don't even have to analyze the structures of NH4 plus and of CO3 2 minus and of NO3 minus nitrate. You don't have to even analyze those structures. They are always, always polar.